So welcome back. In this video, I thought we'd do something a little bit different. Instead of giving you theory, we're going to work a couple of examples, and I'll show you a couple of details in the realm of frames and machines. All right, so the first example that we have set up for you here is a kind of an A-frame type of apparatus that contains a pulley that is supported by a weight that wraps around the pulley that is then anchored here at the bar on ABC. Okay, the supported A is fixed. Okay, our pulley has a radius of 0.1 meters, and then you can kind of see the dimensions. We have a 0.9 and a 1, and then it is 0.8 from the center of the post over to the weight, and the weight weighs 100 kilograms. Okay, what we want to try to find, just kind of as part of the exercise, is we want to find the forces that are acting on the pin at B. That's at this point here. So this is one piece from A, B, and C, and this pin is in the middle. Okay, so we know that makes this a frame and machine type of problem. Okay, and then just for good measure, we're going to also go and try to find the force in CD, and we may do a couple other things along the way as we go. All right, so as we talked about with frames and machines, the strategy for us to solve this problem consists of blowing it apart at all of the hinge locations, because the secret, once again, is to come in and understand the forces that are happening on the pins. All right, so what I've done is I've gone through and I've drawn the basic free body diagrams that will be needed to solve this problem. Okay, there's actually 4 different ones that we want to look at. Okay, and in no particular order. Realistically, the first one that we should do is the pulley, because pulleys are always statically determinate. Okay, and so we've got our pulley, and here's our weight, 100 kilograms times gravity. Okay, that's going to be 981 newtons. Okay, and that's our pulley, and we know that if this pulley is assumed frictionless, which in this problem it is, that the 981 here is matched by a tension in the rope at whatever angle this rope is, also in the amount of 981. All right, so again, the angle doesn't matter. Okay, if this had been a frictional pulley, if it had friction involved, then we would be worried about the wrap angle and where were the tangent points, but for us, that's not a concern at all. Okay, the next piece that we want to look at breaking apart then is bar CD. Okay, and again, it's a straight member, it's pinned at the ends, and then there are no loads. So this guy is actually an axial loaded member. All right, so I could have come in and I could have drawn this as, you know, BX and BY acting that way, and then I'm matching DX and DY on this guy, and then but I decided that since it's an axial force member, one of the tricks that we can do on this guy is it's always simpler, instead of doing the pin, is to write it as an axial force on this. So I assume the member was in tension, which when I go look at the node at C on one of the other members, you'll see that it flips direction. In fact, we'll do that one next. All right, so if I go over here, this is going to be our bar, our vertical bar, ABC. All right, so it's a fixed support. So we're doing our Y's again. No, W is for weight, I is for internal forces, S is for support reactions, E is external, and we're kind of running down the checklist here. So our support reactions are the moment at A, the horizontal at A, and the vertical at A, because it's a fixed support. Okay, at B we have our pin forces. All right, so I've arbitrarily chosen down for BY on this member and over to the left is BX on this one. What that will do is that when I go and I look at this bar BD, these guys will flip on the end of that, and you'll see that one here in a second. Okay, and then for the tension in this bar at C that we have happening up and to the left, now I have it also acting down and to the left at point C on this guy. Okay, because again, what's happening at the pin has to be in equilibrium on both sides, so that's why these things are equal and opposite. Now, we know the angle of this force is 45 degrees based off of our dimensions, that it was 0.9 from B to C, and then it's also 0.9 from B to D. Okay, because we know it was 0.8 from here, and then there's another dimension that told me that it was also 0.9. So we know that it's 45 degrees. Okay? All right, now, the last piece of what we're going to look at then is the bar down at BD. Okay, so this should be no surprise, kind of like what we've done in some of the other videos. Get this up here where you can see it. Okay, and so kind of the same basic game is we have our straight bar, it's pinned at the ends. All right, and so this guy gets the opposite of all the other things that we drew. All right. So again, the straight bar, we have BY up, BX to the left, which means then that those would be the opposite of what we assumed here. BX to the left, BY down, so we're doing the opposite on the other side. Okay, and then EY down, EX to the left will match the centers of the pulley, okay, and then the TC, because we assume tension here, the TC is also tension. It's also oriented at 45 degrees. Okay, now there is one thing I need to go back and show you back on that bar ABC that we forgot. Okay, and that was, we talked about the reaction at A, pins at B, and the reaction at C, but there's also this guy right here, this TW, what I call TW. And what that is, that's the force from the rope, because when I pulled the pulley out, I had to cut the rope. Okay, and so again, that has to balance this. Okay, so this is the one that you often overlook. It's really easy to miss him, so make sure you get that one in there as well. Okay, all right, now we've got all our valid free body diagrams. What we can do is we can now go in and start solving for things. Okay, now we'll do these in kind of a no set order. So if we want to find, say, the force in bar CB, which is this TC force that we have on here, the easiest way to do that then is to come in and try to figure out, well, which one of these has information that I can start to kind of work with. Now, remember, pulleys, the pulley that we have here, I can find all of the reactions on the pulley. That's why we want to start with him, all right? So if I do a force is X equals 0, I can find out that EX, if the horizontal is 981 to the left in the rope, then EX is acting as 981 to the right. No major problems on this picture. Okay, and then likewise for FY, if we're pulling down with 981, now EY is going to be 981 to match in the other direction. Okay, all right. So once I have that, then we look at the pictures that we have. That first picture of the vertical bar that has TC in it, there's just a lot going on here, right? I don't know BX, I don't know BY, I don't know any of the A stuff. There's 5 unknowns, well, 6 if you count the one that we're looking for. So there's just really nothing I can do. So we're going to steer clear of that, remember. But let's go see if we can find some of the others. Okay, this one clearly I can't do anything with because, they're the same value on either side, and there's nothing that I can do to, sum a moment or do something to knock that out. So this one doesn't get me where I want. So the only option that's left with us is to come down to this bar. This guy has TC on it also. Okay, now, so what we can do is if you look at what you know EX, you know EY, and we know TC, but I don't know these two guys at B. All right, and so what we can do, and I've illustrated the dimensions on this, that even though the dimensions for the pulley, the dimensioning on this is one of the tricks that can get you, on a class test or, the fundamentals of engineering exam or something, you got to watch out for these radius of the pulleys, right? Because the dimension that was given was from the center of the bar to the weight. All right, so these forces, when I go do it, because the radius was expressed as 0.1 meters, it's actually back 0.1 meters. Okay, so that's why it's 0.8 minus 0.1, or the 0.7 that you'll see here. All right, so that's 0.7, and then I know that it was 0.9 for the overall length, so that left 0.2 on the other part, and now we've got this picture that we can work with. All right, now the most useful of all the equations in solving this is often the moment equation, because even though I don't know BX and BY, if I choose the sum moments right here, then I can find everything else that I need to know, because EY and EX are not a concern. We know those, and we know their location. It's this TC guy that I don't know. So to find TC, I can turn around and I can sum moments here. And likewise, if I wanted to, I could come in and to find BY and BX, I could find BY by summing moments here. Okay, so there's lots of different ways to tackle these problems, and all are equally valid. All right, so if we go through and we do that, this is the equation. It'll be a minus EY because EY is down and I'm summing moments here. So again, I'm assuming counterclockwise positive. That's our right-hand rule convention. That's the one that says I'm going to assume positive to the right or positive up and counterclockwise positive to get you to that one. All right, so we go in and we do a minus EY times 0.7. That's this distance. EX doesn't do anything. BX doesn't do anything. BY doesn't do anything. So I'm not even going to write those in the equation. Okay, now we do have this angled force here, okay, and again, since I don't know the perpendicular distance from this point to wherever this guy's line is, okay, I'm going to break him into components into a vertical and a horizontal. All right, so the vertical component is TC sine 45 degrees, and it will be acting up this way at C, okay, and then I'm going to multiply it by its distance of 0.9, and that's going to be going in a counterclockwise direction, so that's why it goes in as a positive. But remember, if I split this guy into two, I got to consider both. Okay, now this bar is horizontal, so the TCX is horizontal here. Okay, and if you look, it's actually acting through the point, so that's why he doesn't show up, but I did consider him. All right, so if we take a force and break it into components, remember you always have to break it back to two components. Okay, so then I can go through and I can plug in all my values. I can do a little bit of algebra, and what I find is that TC comes out as a positive 1,079 newtons. Okay, which means that because it was positive, it matches the direction that I assumed on the picture. So if it's positive 1079 and I assume tension, then that's why it's written as a tensile force, and that's how you find the force in the bar. Okay, all right, now if we come through and we can then take that same picture and to find Bx and By, again, there's lots of different ways to do this. The easiest one is to probably just keep playing with this piece here and doing a sum of forces x and a sum of forces y. Okay, so forces x is going to be bx to the right minus ex the way that I drew it minus this tc x component guy. All right, so that's why what you're going to see is, positive bx minus ex minus tc cosine 45 degrees all equal to 0. I now know TC as 1079. I know EX is 981 from the pulley, and so I can solve for BX as being a 1740 newtons. Okay, and then in a similar fashion, we do sum of forces in the y direction. So I'm going to do BY up, EY down, and then TCY, the y component of TC acting up. So positive BY minus EY plus TC sine 45 degrees all equal to 0. And again, I know E, I know TC. I can find BY. So BY is 218 newtons acting on that one. So it's not too hard. Like I said, there's lots of ways to get there. It's just kind of a matter of drawing the pictures and seeing what you know and seeing how do we start to kind of progress our way through this particular system. Not too bad, not too bad. Okay, now let's take a look at something a little bit differently that you can do. Okay, you notice that we blew this thing apart into lots of different pieces. Okay, so I can take the same problem. This is the original picture that we had, okay? And so one of the things that we would like to do right off the bat, if we can, is we like to draw a free body diagram of the entire system. Because sometimes what can happen is I can actually find AX, MA, and AY, right, support reactions. And if I know those, then maybe that would have dictated that I could have gone to the free body diagram of ABC. It's an extra step, and it wasn't necessary in this problem, but a lot of times this is what I like to do. Okay, now you'll notice that the picture that we have drawn here, again, if we do our y's, okay, the weight would be that 981 acting here, so we've got that. There are no internals because I cut nothing. Right? I didn't cut the bar, I didn't cut the rope, I didn't pull the pulley off. Okay, so there is no internal. The support reactions are these three guys to the right and up and counterclockwise for our values at A. Okay, and then the external forces we didn't have to worry about because we accounted for the weight of the box. Okay, so, all right. So now, for fun, suppose that you wanted to find the reactions at MA. Okay, we're going to show you kind of an alternative way to do this, all right? So from the whole free body diagram, which was the picture that we just showed you here, you can see that it's pretty easy. If I sum moments at A, AX goes away, AY goes away. The only thing left is this moment at A. And the only force that happens is this 981. So all I need to know is the distance, the perpendicular distance from the line of action of this force, which is vertical, and which we know is 0.8. It was given to us. So we know everything. So I can find MA without cutting anything. Okay. And so if I do that, and that's what we're going to look at in here, is that sum of MA is equal to 0, MA minus 981 times 0.8. All right. Now, from that original picture that we had of ABC, let's see if I can get this up here where we can kind of, if you remember, from this guy, I can write the same equation. You can see it's a whole lot more complex coming through this. I can still find the values. I got BX to the left, BY down, and here's that force in the rope, and then I've got my TC. It's doable, but the math becomes a lot more cumbersome to be able to find our values. So from ABC, by some moments at A equal to 0, I do AX times 0, AY times 0, BY times 0. Okay, I'm now taking the vertical component of that force in the bar. Okay, which again was this picture here. So we're taking the vertical component of this guy, which is through the line, so it gets multiplied by 0, but then I get the horizontal piece, which is now by the whole dimension of the bar. Okay, so if you look, the vertical component of this piece is TC sine 45 times 0. Okay, I have my BX reaction force that's times 1 because that's the guy that was acting horizontally here on that original picture. Okay, and then I have the TW, which was the rope that was cut, times it's 1.1 because, again, the location of the rope is 1 meter plus 0.1 gets me to there. Okay, and then I get the X component. minus TC times the cosine of 45 times 1.9 plus the MA reaction that we have happening there. And so if I plug in all of my math on all of this thing, I end up with an MA of 788.7 Newton meters. Okay, now you notice the number's slightly different than what I had happening up here. And part of that gets into that numerical sensitivity issue that we talked about. Okay, anytime these trig functions start to sneak in, okay, or I take, start taking whole numbers, multiplying by decimal values and start rounding, things get a little ugly. And cosine of 45, we know is 0.707, and then a bunch of decimals. If I round that off, that's the cause of this difference. Now, in the grand scheme of things, it's not a big difference in engineering, but if you're doing microfine measurements, you got to be very, very careful of the numerical sensitivity of this. But for the purposes of this exercise, we'll say these are close enough. Okay, and so we'll call it good, if you will. Okay, all right. Okay. Now, on to another example, okay? Now, the next example, okay, is the problem I warned you all about last time, okay? And these are those old hand tool problems that are just not hard, but they're just kind of, there's just a lot to them. Okay, this is kind of a rite of passage problem that every engineer has solved at some point in their life. Okay, it's generally an exam question, or it's just one of those homework problems that they spent 3 pages writing trying to get equations to work, and they could just never get it to work out. It's just the first time out, these are kind of rough. All right, so this is an example I found in a textbook that we'll kind of work our way through. And what this is kind of like a pair of vice grips or kind of a hand clamp kind of thing. And so we've got this hand clamp. That's pinned here, it's pinned here, it goes over, and then it's clamping down on this little ball bearing kind of thing. It's exerting a force. And then there's a lever that goes from here all the way up through this pin into this pin. Okay, and then there's a diagonal that's also part of the locking mechanism that also helps transmit a lot more force into the apparatus. Okay, now if we look at some of the dimensions, I've got 12 millimeters, 120, and 36. Okay, we know that the bearing or the round object that it's grabbing hold of is 30 millimeters wide. Okay, and then we know that we also have a 6 millimeter distance that goes from the bottom of the bearing to this line of the first hinge. Okay, all right, so if we go through and we look at some of the other dimensions, I've got a 96, I've got a 30, and I've got a 42 millimeter happening on that. All right, so just like the same approach, okay, this is clearly a frame of machine. It's got a lot of hinged parts. And so all we want to do is that if I put a force P here, can I find the force that's being clamped at the bearing? Okay, on this, okay? And so just as you thought, okay, we're going to blow this thing apart at the hinges, but there is one extra piece that shows up when we do that, and that's the bearing itself. That's this guy. All right, okay? And the reason that I need him is because I have to pull him out in order to be able to see this clamping force. Okay, so I know that as I squeeze on the lever, the clamp puts the pressure on the top of the bearing and puts the pressure on the bottom, and it's these two guys in equilibrium that cause this guy to kind of stay in place. All right, so now once I have that done, I can go and draw my second free body diagram, which would be the first piece. Basically, I cut all the pins as I start to look at it, and I get this weird looking upper half of the tool, right? And so I've got a P force acting down. I have two forces, AY and AX, happening at this position. I have a BY and a BX at this one, okay? And then I get this clamping force, which is the opposite of what we had over here on the bearing. All right. Not sure why the focus keeps going out. Let's see if that helps. All right. Okay. So we can dimension this accordingly with all the dimensions of the apparatus, and then I can go in and I can look at the second piece of the apparatus. You can see that's the lower jaw. It's the one that involved this pin, and then the bottom of the bearing. So you get kind of this rhinoceros horn looking thing. Okay, and all we're doing is we're taking BY and BX opposite of what I assumed the first time I drew them, which was up here. Okay, my clamping force is down on this guy. Okay, and then dy and dx, since we haven't seen those before, I just assumed up and to the right. Okay, and so then we have all of our dimensions. Okay. On those. Okay, and then we get the diagonal. We play the same game. We've already seen AY and AX, so that's why they're opposite. It was up here and to the right here, so now it's down and to the left. And then I have cy and cx here, and then their appropriate dimensions. Okay, and then the last piece that you would have would be looking at number 5. Okay, and this is the lower handle. All right, so here's my p force up. I get my cx and cy opposite of what I drew over here. Okay, and then I get my dy and dx opposite of what we had on this guy. So I zoomed up and to the right, so now it's down and to the left. Okay, and those become all of the pieces. And again, we can figure out all the dimensions from the geometry of this. Okay, the question becomes, where in the world do you start? All right, so what we're wanting to find is the actual F clamping force. So I have two paths. I could either work off of the top piece or I could work off of the bottom piece. Okay, and so one of the things that I look for, okay, they both have a ton of unknowns happening on them, right? Okay, assuming that we know the value of the force P, since our answer is going to be in terms of P, I have 4 unknowns on this guy, okay, and I have, if I know P, I have 5 unknowns on the upper, okay, but what happens in this, and again, kind of depending on how you choose to tackle, there's a bunch of different ways. This guy looks like a prime candidate because if I sum moments at either A or at B, I will knock out all of the forces. So say I chose B, I would knock out BY and BX, but I would also get rid of AX because it's along the same line that goes back through this point. Okay, whereas if I chose to go to the bottom one on here, there's actually this little 6 millimeter offset that happens. So even if I sum moments here, I still get both CY and CX. Or vice versa, if I sum moments here, I still get dy and dx on them. Okay, it's not quite as clean cut for what it is that we're trying to do. All right, so the way that I chose to solve this, we come back and I slide this up where you can see in part 3. I chose to start with the lower portion. Okay, now the only reason I did that is I needed to start somewhere with my F clamp force, right? And this piece just looks a little bit simpler than the one that we have up here. Okay, I'm going to have to work with both eventually anyway, but that's kind of the reason I chose to go there. So what I did is I chose to sum moments, okay, on this piece number 3, and I chose to sum the moments at the B location, all right? And what that generated for me was it would now generate an equation that looks something kind of like this. All right, I get my dx times 36, so that's my horizontal force times this 36 dimension. I get my dy as a negative because it's going in the clockwise direction, multiplied by the 6. And then I also pick up my F clamp force also multiplied by 36, and all that better be equal to 0. That's the first equation that we would have to solve this thing. Okay. The next one that I would go to, then, is since I have D, and I'm trying to find relationships, I can get to P by coming in and looking at picture number 5. Okay, and so what we would do on this case, since I have my expressions for the D's, and I want to keep a P in here, I'm going to choose the sum of moments at this to knock those two guys out. So it's that same trick. You choose your moment equation, and you knock them out by summing moments over the top of them. So what I'll end up with is then this dx guy times a 6, and a dy times a 30, and this P times 96. Okay, and so you can see that that's the equation that shows up when I do that. All right, so it's a minus P times 96 minus dy times 30 plus dx times 6 all equal to 0. And so what we've done is we've set up a set of equations in this, okay, in which I have the same two unknowns, dx and dy. I have my F clamp that I'm looking for, and I have the P that would be assumed to be unknown. So this is realistically two equations, with the same two unknowns. It's, I can't solve for all of them, obviously, but I can generate some expressions. So what I did, in order to be able to knock these things out, I just used a little bit of some of our algebra tricks where I can scale up one of these, and I can knock out the other. Okay, and so what we did is we chose to take, I chose to get rid of the dx up here, and it's because if you notice, I have a dx times 6 and a dx times 36. If I choose to multiply everything in here by minus 6 on here, then I can add this equation to that one, and the dx's and everything will start to fall out. All right, and so that's what I did. So I took a minus 6 into this, so now it's a positive 6p times 96 because it was negative before. It was a plus 6 dy times 30 because it was negative before. Okay, I now have minus 6 dx times 6. Okay, and then I have equals to 0 times a minus 6. Like I got to multiply both sides, so I'm just basically scaling that equation up. All right, and so then I take this equation and I add it back to this equation as we start to kind of look at that. And when I do that, the equation that falls out then is going to be equal to my minus F clamp, okay, times 36, okay, minus dy times 6, okay, plus dx times 36, okay, is that equation. Just kind of rearranging things so that you can see how things will cancel, all equal to 0. Okay, and then when I add all this stuff together, you can see that these two terms now knock each other out. All right, and so all I'm going to do is rewrite this 6p times 96 minus my 36 times f clamp. Okay, and then I have 6 times 30 minus 6, that's the 174 dy, and so what you can do is you now have an expression for finding dy. Okay, and with dy, I can do a little bit of algebra rearranging, and you can see that it gets a little ugly, and the algebra gets a little nasty, but it's not overly difficult on those, okay? And so once I have dy, what I can do then is I can then go back up to my piece number 3 on here, okay? And if I have dy, I can now find by, okay, by doing a sum of forces in the y direction, okay? And what that does for us here is I have, we're going to blur it again. Okay. Is I can do a sum of forces in the y equals 0 up, so by plus dy minus my f clamp off of that piece, so I can solve for by in terms of that dy, so I can actually get an expression for by, you know, in terms of just kind of doing some simple rearranging. You know, and so this guy, again, a little bit ugly, but not overly difficult. And then I could jump up to, you know, up to the upper bar at number 2 and do a sum of the moments at A. If you remember, the bar at number 2 was that first guy. All right, and so if I have by and bx is in line, if I sum moments here, then I can write an expression for p. Okay, and that's the reason I chose to go back up to 2. Again, there's multiple ways you could do this. You could work it by solving off the bottom one as well, but that's just the way I happen to choose to go. All right, and so all that's left then is to write the equation for the sum of the moments at A. That's going to be 12 times P, okay, plus a by times 120, okay, plus bx times 0, because again, this guy was acting through the line, and then I have plus f clamp times 156, all equal to 0. All right, and then what I can do is I can then take this big monster equation by, and I can bring him down in to here. Okay, and when I do that, now I've got everything in terms of P and F clamp. And with a little bit of algebra, I can solve for F clamp in terms of P, which I'll leave that as an exercise for you. I just wanted to kind of show you some of the tricks and techniques on how we can do this. Now, like I say, you know, we chose, in this picture, we chose to start off at 3, okay, and then get our dx and dy, and then use that to get to by, and then to come back up to here. I could have just as easily gone and looked at the lower piece, right? But the problem that we had with that is, again, because these two guys weren't lined up, okay, when I sum moments here, the dx is going to show up, and I didn't have an equation out of this picture for dx. So that's why I chose to go back up to the top. So those are the things you're looking for. You're looking for places where forces cross and where you can knock out more than one of them with, you know, a single moment equation, kind of like what we did with the, you know, the method of sections back when we were doing trusses. So anyway, that's kind of the ugliness that is these hand tool problems. Okay, and like I say, most professors are sadistic enough that they will give you a problem that looks something like that. Hopefully not 4 pieces, and you'll notice that, you know, at least this one had things in a line where I could choose to look for that, okay? But everything else, nothing was lined up. Even on this rhinoceros horn here, by and dy didn't line up. If these had lined up, this would have been a whole lot easier, all right? I could have come in and I could have, you know, picked off an equation for, you know, for dx by summing moments. I mean, there's any number of ways that you can do this. You can go, you know, a lot of different paths as you start to go through this, right? You know, I could choose to come in and play with this, but again, because it's on an angle and none of the forces are places where I can knock out more than 2 of them, Okay, it just wasn't the most practical application. So that's one of the things that you're looking for as you try to start to solve this. So anyway, I apologize for the focusing issues. Hopefully it wasn't too distracting. And with that, we will call it a day. So anyway, as always, if you're, if you've got any feedback or ways that we can make these videos a little bit better, please leave a comment down below. And as always, be sure to subscribe to the videos, and we'll try to keep the content coming. So anyway, thank you very much. Have a good evening. Bye.